Studying gases was all the rage in the 18th century. Over in France, the chemist Antoine Laurent Lavoisier, often called the father of modern chemistry, had been intrigued by an experiment that a friend of his had performed with a yet unnamed type of gas. Lavoisier replicated the experiment and decided to call this unnamed gas oxygen. Around the same time, English chemist Henry Cavendish was burning a different unnamed gas within an oxygen-rich environment, collecting a bunch of water that was made in the process. Lavoisier then repeated Cavendish's experiments using an electrical spark and named this other new gas hydrogen. And if you've ever seen photos of the Hindenburg disaster, you know an experiment like this can be very dangerous. Thankfully, Lavoisier didn't blow himself up, but he did successfully demonstrate that water was made up of these two gases, hydrogen and oxygen. Since then, we have learned a whole lot more about water and its amazing life-sustaining properties. Also, we stopped putting hydrogen in blimps, so, win-win on that one. Hi, I'm Dr. Sammy, your friendly neighborhood entomologist, and this is Crash Course Biology. I'm glad you're here. Could I interest you in a cold glass of theme music? Water. It's in your bathtub, your slip and slide, your favorite swimming hole, and your preferred brand of seltzer. And it's in you. Whether you notice it or not, water does so much more than keep you hydrated. So today, we are writing a love letter to the most underrated of beverages, which is so much more than just a beverage. Our one and only H2O. First things first, water is an ingredient in so many other things. But what are the ingredients in water? I mean, chemically speaking. Can we rewind a sec? I think I just said them. They're H, hydrogen, two of them, and O, oxygen. If you've ever played a tug-of-war with someone a whole lot stronger than you, then you know how hydrogen probably feels when it shares an electron with oxygen. Oxygen takes hold of hydrogen's one electron, sharing it to form a strong covalent bond. And then it just starts pulling. And it's in that push and pull between oxygen and hydrogen that water is formed. You know how two magnets with the same polarity will push each other away when you try and bring them together? That's what these negatively charged electrons do too. They repel each other, which gives water a bent V shape. At the same time, oxygen attracts the electrons, making these bonds with hydrogen. Oxygen is stronger, so at any point, the shared electron is going to be hanging closer to the O than the H. This push and pull gives hydrogen a slight positive charge and oxygen a slight negative one. And the partial charges on either side of a water molecule make it a polar molecule. At this point, you might be wondering, wait, aren't we studying biology? Why is it getting so gassy all of a sudden? Well, that's because this polar characteristic of water has helped it sustain life on Earth for over 3.7 billion years. So in our love letter scenario, water's polarity is what makes it the romantic lead. There are all sorts of properties that follow from that polarity. Like, because water is water and water is polar, it has so many other characteristics that make us love it. It may not be smart, funny, or kind like a true romantic lead. But instead of personality traits like humans, it has its own special property. One of the most remarkable is its function as a solvent. Like, water is really good at dissolving things like sugar or salt. But then there are other molecules that don't dissolve in water. The way that water dissolves some molecules and doesn't dissolve others helps cells take shape. You've seen water's polarity acting outside of your body too. Like, you know that cute thing that water does where it won't stay mixed with the oil in your salad dressing? That's polarity. Polarity is pretty picky about who water makes friends with. It prevents non-polar lipids like fat from dissolving in water. But then there are chemicals like table salt, which becomes really soluble in water by breaking apart into full-on positive and negative particles called ions. Water's polarity helps it dissolve these ionic salts, the partly positive hydrogens of water hanging out with the negative ions, and the slightly negative oxygens group up around the positive ions. This allows chemical reactions to occur that help organisms like us convert food and drink into energy or metabolize. So water can't stick to non-polar stuff, but it can stick to stuff that is polar, or charged. And since water itself is polar, it sticks to itself too. A partially negative oxygen atom in a water molecule attracts the partially positive hydrogen in another. So no matter if it's the liquid water in an aquarium or solid water in a glacier, water molecules are going to stick to other water molecules. But let's pause on that solid water for a moment. Water's cooler alter ego ice has some interesting qualities too. Like, have you ever wondered how fish stay alive in the winter if their home freezes over? Well, those fish can thank solid ice for insulating the liquid water, keeping it warm enough down below for them to just keep swimming. To you, it probably seems totally normal that ice floats. You saw it happen already 3 times today with your water, your tea, and your orange juice. Wait, who puts ice in orange juice? Scratch that one. But it's actually super unusual because solids are usually denser than liquids, so they sink. But because the water in ice makes more hydrogen bonds than liquid water, they space themselves out more than in liquid water, which makes ice less dense, allowing it to float. Just another charming quirk of our favorite liquid. Of course, no great love story would be complete without a little tension. Well, water has us covered there too. Water has what we call surface tension. The hydrogen bonds that exist on the molecular level create a self-sticking effect called cohesion that creates that tension. Few understand this amazing feature better than the humble water strider. Well, I mean, it can walk on water, so it's probably not that humble, but you know. See, this fancy little insect seemingly performs a miracle by taking advantage of surface tension. Using its long legs to strut across the surface of the water, it's able to make this look easy thanks to that cohesion formed by the hydrogen bonds. And similar to cohesion, which lets water stick to itself, adhesion lets water molecules stick to other molecules. Like when I actually remember to water my houseplants, adhesion, with some assistance from cohesion and surface tension, lets the water stick to the inside of the plant's vascular system to be pulled up and nourish the topmost leaves. Oh, and I can't move on without talking about one of water's most interesting forms, water vapor. For that, we have the awesomeness of evaporation to thank. And that's more than just the sort of evaporation that happens when you leave a cup lying around and a week later it's empty. And BT dubs, we tried to make an evaporation joke here, but have you ever tried to make a joke about evaporation? It is literally like watching paint dry. Oh wait, that's a joke! But it's also what happens when you break a sweat jogging, and your body uses the water evaporating off of your skin to help you cool. The evaporation of water through sweat is really good for us water-based life forms because it makes us more resistant to temperature changes and helps us regulate our internal systems. And that ability to self-regulate is a universal characteristic of life. Water does us yet another solid when it evaporates from oceans and lakes and gets transported through the air and then falls back down as rain. When it's still up in the air, before it comes back down as rain, water buffers drastic temperature increases that would be caused by the sun's energy. Likewise, at night, the water in the air prevents extreme drops in temperature. So all this time, we've been talking all about how great water is and how important it is for life, but be honest, when's the last time you really stopped to consider water? I mean, is it really all that special? What would happen if we swapped it out for, I don't know, for example, ethanol, a type of alcohol and a renewable fuel made from corn? Let's just say things would get real tough for life on Earth real quick if that ever happened. Since ethanol forms way less hydrogen bonds than water does, it would evaporate much quicker, drying up lakes. And our buddy the water strider would need a new name. Maybe the ethanol sinker, since ethanol has much lower surface tension. If they tried to walk on it, they'd fall right in. Without the strong adhesion of water, plants would be unable to get enough of it into their systems. Ethanol just falls short of H2O. And like the beautiful new neighbor in a rom-com, water is something you just can't help but compare other things to. But in water's case, it's a lot more formalized. We have a whole system and everything, and that system is called the pH scale. We use the pH scale to tell us how acidic or basic an aqueous solution is, or a solution that has water as its solvent. That might sound complicated, but you've encountered these substances before. Some of the prime acids in your life might be lemon juice or vinegar. And there's stomach acid, which helps us break down food and burp the alphabet. There's some of the strongest acids out there. At the other extreme, cleaning products like bleach, ammonia, and oven cleaner are bases, which, safety alert, you probably want to wear gloves if you're using any of those. Water, meanwhile, has a neutral pH, sitting right in the middle of the scale at lucky number 7. And here's how we get these different types of solutions. Occasionally, water molecules split apart, with one hydrogen popping off and leaving its electron behind. This creates two ions, a positive hydrogen ion, H+, and a negatively charged ion, OH-, or hydroxide. Acids increase the amount of hydrogen ions in water, while bases increase the amount of hydroxide ions. You might think of acids as dangerous, but that's only true in extreme cases, like how the sulfuric acid in a battery can cause chemical burns. But our skin is adapted for a little bit of acidity, so you won't notice a little lemon juice on your hand. Unless, of course, you have a cut there. And you may think of bases as safe, but like I mentioned, basic substances like bleach can be super dangerous. It's interesting though, our blood is actually slightly basic. And that's no shade to our blood. As any vampire would tell you, our blood is pretty awesome. Like so much of life, it all comes down to regulation, how our bodies keep themselves situated in a healthy balance. In this case, right on the middle of the seesaw of the pH scale. So for example, when our bodies make carbon dioxide, the stuff we exhale, it can decrease the pH of our blood, throwing us off balance, chemically speaking. But our bodies have what's called chemical buffers, which resist changes in pH. And when you're talking about your blood, well, it's pretty important to get that balance right. Now, blood is great. We'd be lost without it. But blood would be nothing without water. So water, we love you. We've known you our entire lives. Heck, we are made out of you, for crying out loud. Without you, things would be pretty bad for us. And for all living stuff here on Earth. You're so valuable to us that you're the first thing that scientists look for on other planets as an indicator of life, past or present. So yes, you're a tiny molecule, but you're also a vast ocean. You're a heavy rainstorm and a sip of hot tea. And if that ain't a love letter, I don't know what is. Heck, I would very much like to borrow that line for my wedding vows someday. In our next episode, we'll learn about how a little invention called the microscope has helped us better understand the smallest living things around us. I'll see you then. This series was produced in collaboration with HHMI Biointeractive. If you're an educator, visit biointeractive.org/crash course for classroom resources and professional development related to the topics covered in this course. Thanks for watching this episode of Crash Course Biology, which was filmed at our studio in Indianapolis, Indiana, and was made with the help of all of these nice people. If you want to help keep Crash Course free for everyone forever, you can join our community on Patreon.